So good morning, all. This morning's first speaker is Hajime Ishihara from JICE, who worked with Eric on various topics, and is going to start by saying a few words about the workshop last year that Eric organized in Stockholm. Thank you.
Okay, this is the homepage of the workshop Eric organized August last year. I would like to say something on or a story concerning this workshop before my talk. So I, together with Japanese colleagues, I have been running project on mathematical logic and its applications, supported by JSPS, Japan Society for the Promotion of Science, with the people in Sweden, Germany, UK, and Italy, and France. Since the, exchanges with Sweden is less than with other countries, so JSPS pushed me to increase number of exchange with Sweden. So I proposed Eric to organize a workshop, in a sense, joint workshop in Sweden, to increase the number of exchanges. He kindly agreed and he organized this workshop. It was quite nice workshop, and we say Japanese participants enjoyed very much. So we have to thank again Eric and the local organizer, including Peter. And I would like to say something concerning Eric. So the night before the opening day of the workshop, Eric and Satoshi, I don't know if he's here or not, Satoshi and I went to a Man in the Moon, a pub in the center. And there we enjoyed, a couple of several beers before dinner, and quite nice Swedish dishes, and a couple of schnapps after dinner. But we remember it as if it were yesterday. But we are very sad that we will never have next occasion with Eric in Man in the Moon. So he was a real and excellent scholar who was quite considerate of the feelings of others. Okay, I would like to say again, thanks for Eric. So please let me start my talk. How do we do this? Okay. Okay, can I? Okay, I'm going to talk about yet another predicative compression of a uniform space. This is why yet another, because the in February 2008, Eric Palmgren was visiting JICE, and also Peter Schuster was visiting JICE, and Josef Berger was staying at JICE as a postdoctoral fellow. And we are working on completion of a uniform space. The collaboration had led to the paper, joint paper with Eric, a predicative completion of a uniform space, which appeared in Annals of Pure and Applied Logic. So our motivation was, so if you look into the Bishop's book, Bishop introduced a constructive notion of a uniform space with a set of pseudometrics and constructed the completion of a uniform space by means of the set of Cauchy filters. The construction of a set of Cauchy filters is problematic from a predicative point of view. So we try to construct a completion in a predicative setting. So we pointed out the notion of uniform space with entourage has an advantage over the one with pseudometrics. This is, we gave an extreme example that is discrete uniformity to show that discrete uniformity could not be given by a set of pseudometrics. But I'm going to give another very constructive, another example of such example, another such example in a later of my talk. And we gave a predicative completion of a uniform space given by entourages in CZF, the constructive and predicative Solomero-Frankel set theory founded by Axel. In this talk, the notion of a uniform space with pseudometric has many applications in other areas of constructive mathematics. Actually, the second half of this talk is devoted to give such an example. We give a predicative completion of a uniform space with pseudometrics by means of the notion of a net. In elementary constructive set theory, ECST, with exponentiation action, which is a subsystem of CZF. Notion of net is a generalization of the notion of a sequence. So the completion is a generalization of an parallel to the usual completion of a metric space. If you are familiar with the construction of completion of a metric space, for example, as in Bishop's book, it is quite easy to understand this construction. So before giving our construction, I would like to give some quick overview, quick review of set theories and construction given by us with Eric. So the set theory, ECST uses intuitionistic logic, of course, and has a set theoretic actions, extensionality, pairing, union, replacement, and bounded separation. Bounded separation is something like usual separation, but the formula is restricted to bounded formula. Bounded formula is all quantifiers occurring in it is bounded. That is, that is in this form, okay? And ECST has strong infinity as an action, which said that we have the set of natural number A and mathematical induction for, not for all formula, but for set, okay, set. The class of total relation between set A and B is denoted by MVAB. relation R is in MVAB if it is a relation and total. The class of function from A to B is denoted by A to DA, B to DA, which say that the F is total relation and single valued. That set theory sees that F is obtained from ECST by replacing replacement by strong collection. It's something like removing uniqueness condition from replacement and further strength. And adding subset correction and set induction. In ECST, subset correction, the additional action implies so-called fullness, which say that for any set A and B, there is a subset of the class of total relations such that for any total relation, there is a total relation in C, which is a subset of R. And fullness and strong collection implies subset collection. And the notable consequence of fullness is that the function space form a set. Just use bounded separation, just apply bounded separation to C to separate single valued relation. Then we know that function space is a set. So uniform space, this is the definition of a uniform space with entourages. We adapt the base of entourages. So uniform space is a pair of a set and a set U of subsets of product space, which is directed downward, and each element of U contains diagonal set. And it's something like balanced. For any U, there is a V. V is contained in inverse of U. And for any U, there is a B. The composition of V to V is contained in U. This is the definition. And we assume in the following, we assume any uniform space is T1. That is this condition. So if for any X and Y, and for any U, X pair of XY is in U, then X equals Y. So I'm going to give an example of a uniform space given by entourages. So before that, we need some definition. Normal space defined as usual, and normal space forms a metric space with the metric defined in this way. And Banach space is normal space, which is complete with respect to this metric. And typical examples is a sequence space called small LP space, which is a sequence of real number such that this series converges. And the norm is defined in this way. So we know that LP is separable Banach space. And linear functional F1 norm space is bounded if this set is bounded. Here, BE is a unit ball of E. A linear functional F1 norm space is normable if this soup exists. This soup exists. And usually, classically, the dual space is defined by bounded, the set of bounded linear functional. Because classically, every bounded linear functional has its norm, but constructively not. So we have two sets, E star, the set of bounded linear functional, and E prime, set of normable linear functional. And we have the following propositions. Every bounded linear functional on L2 is normable, then LPO holds. That is an instance of the principle of excluded middle. And also we have the set of normable linear functionals on L1 is linear, then LPO holds. So that means we cannot assume the set of normable linear functionals forms a linear space. So it is very difficult to deal with the uniform topology on a dual of norm space. But it is given by uniform topology of E star is given as a uniform space U, where U is defined in this way, and each entourage is defined in this way. I think this uniform space could not be given by a set of pseudometrics. So this is very constructive. Of course, classically, dual space is Banach space, but constructively, we have to deal it as a uniform space with entourages, okay? So Eric and we did is the following compression. We construct is the following. A set F of subsets of X is a filter if it is inhabited. Each element of F is inhabited, and F is downward directed. And a filter F on X converges to X in X, large X, if for each entourage U, there is the element A in F such that A is contained in a neighborhood of X defined by U, okay? And a filter F on X is Cauchy filter if for any U, entourage U, there is the element in F that A times A is contained in U. And uniform space XU is complete if every Cauchy filter on X converges. So Bishop's idea was to take all Cauchy filter as a compression, but we don't have power set action in CZF. How to say, the compression would not form a set, okay? So that's a point, a problem. So we want to construct a compression as a set, okay? So our compression is the following. For given T1 uniform space, since X and U are set by fullness, there is a set R, which is a subset of total relation between U and X, such that this is a condition for fullness, and define a bounded formula as follows. For all U and V and for all X and Y, Ux is in the total relation and Vy is in the total relation, then Xy is in this set. And using bounded separation, define X tilde by in this way. Then I will not give proof in detail, but we show that we define ontologies on X tilde appropriately, then X tilde U tilde is complete. And we have usual universal property for the completion. YB, let YB be a complete T1 uniform space, and we have a uniformly continuous map from XU to YB. Then there exists a unique uniformly continuous function F tilde from completion of X to Y such that this holds. I is inclusion map from XU to X tilde U tilde. Okay, let's move to the definition of uniform space with pseudometrics. A pseudometric D on a set X is a mapping from product to the real such that these three conditions hold. Okay. Distance between X is 0 and symmetric and triangle inequality. And a metrically uniform space is a pair X and D of a set X and a family D of pseudometrics indexed by an inhabited set I such that this holds. This is just a T1 condition. We assume metrically uniform space is always T1. And if I is a singleton, then XD is called a metric space. Okay. Here is an example of such metrically uniform space. The weak topology on a normed space is defined as a metrically uniform space, ED, where a family of pseudometrics is indexed by elements of E star dual space, and the distance is pseudometric is defined in this way. Okay, and also we can define weak star topology on the dual space as a metrically uniform space. Thus, a family of pseudometrics is indexed by element of E, and pseudometric is defined in this way. Then we can define a weak star topology on the dual space. Okay. I'm going to give, I told you that the second part of this talk is devoted to an application of metrically uniform space. Okay. So before giving construction of completion, we need some notations. So for set S, we write S star for the set of finite sequences of S with the following notations. Absolute value of sigma denotes length, and epsilon denotes empty sequence. Sigma L denotes the Lth element of sigma, and S in sigma denote, how to say, S appears somewhere in sigma. And star denotes concatenation, and S to the N denote the constant sequence of length N. Okay? And also we define a binary relation on S star by sigma is less than tau if the length of sigma is less than or equal to tau, and each element in sigma is in tau. Then S star with this ordering is a directed preordered set. Upper bound, common upper bound of sigma tau is just concatenation of sigma and tau. And if S is a singleton, then S star with this order is order isomorphic to ordering on natural number by the mapping sigma to the length of sigma and n to the constant sequence. Okay. So, and this is another notation. So for given sigma in I star, I is an index set of a family of pseudometrics. Then d sigma is a pseudometric on X given by in this way, taking maximum. And special case, if sigma is an empty sequence, then we define the pseudometrics always 0. Okay. So next, for uniform space and lambda, I don't know how to read this symbol, but the ordering is a directed preordered set, and any map from of lambda into X is called a net or a Moore-Smith sequence. Okay, and we write something like a sequence with a notation something like sequence. A net X lambda converges to an element of X with a modulus. This is a crucial point. We define convergence and cosiness always together with modulus. Okay. Otherwise, we have to invoke axiom choice. Okay. So therefore, the notion of convergence is defined together with modulus. Modulus is mapping function from I star to lambda, such that if lambda is greater than beta sigma, then d sigma x lambda x is less than or equal to 2 to the minus length of sigma. And we write in this notation as usual to say that x lambda converges to x, and x is a limit of x lambda. And a net is cosinet with modulus. Modulus is the function from I star to lambda. If mu and nu is greater than alpha sigma, then distance between x mu, x nu measured by sigma is less than 2 to the length of 2 to the minus length of sigma. And the uniform space is complete if every cosinet converges. And for a uniform space, we define a regular net X, which is a cosinet on this, how to say, directed preordered set. Okay, this is just with modulus identity. We write X tilde for the set of all regular nets in X. And it is easy to see that pseudometrics could be extended on X tilde by this definition. Okay, this I to the n is a constant sequence of I of length n. Okay, so then, so we can define an inclusion map from of X into X tilde by just giving a constant net. Okay, and we can show the display the inclusion map plays a distance. Okay, this is quite easy. And compression of a uniform space is X tilde and D tilde. D tilde is defined by a family of Di tilde, and equality is given by in this way. So, and we can show that the completion x tilde d tilde over uniform space xd is complete. So, and next we are going to try to prove a universal property. So to define a uniform continuity between metrically uniform spaces, is mapping is uniformly continuous with a monotone modulus. We don't need monotoneness, but it's easy to assume because easy to prove things if we assume monotoneness. Every modulus, we can construct a monotone modulus. So monotonicity is not so important. So uniform, if distance measured by alpha sigma prime between x and y is less than or equal to 2 to the length of alpha sigma prime, implies distance measured by sigma prime of between fx and fy is less than 2 to the minus length of sigma prime. Okay, this is the definition of uniform continuity, and uniformly continuous mapping is a uniform isomorphism if it has a uniformly continuous inverse. And two uniform spaces are uniformly equivalent if there exists a uniform isomorphism between x and y. This is a very technical notion, local uniform continuity, which is roughly speaking, F is locally uniformly continuous if it is uniformly continuous any neighborhood of an element in the completion. Okay. So this is the neighborhood. This is the neighborhood of the completion. So uniformly continuous, locally uniformly continuous for each element in completion. F is uniformly continuous on the neighborhood of X. Okay. So two remarks. If uniform space is given by a countable set of pseudometrics, then it is uniformly equivalent to a metric space given by this metric. So how to say, an interesting case is uncountable set of pseudometrics. Otherwise, we can reduce uniform space, such uniform space into metric space. And the technical definition of local uniformly continuity because of, we introduced local uniform continuity because scalar multiplication over normed space is not uniformly continuous, but locally uniformly continuous. I think I have to be quick. And we can prove the universal property for each. So X is a uniform space and Y is a completely uniform space. And then for each uniformly, respectively, locally uniformly continuous mapping from X to Y, there is a uniformly, respectively, locally uniformly continuous mapping X tilde to Y such that this diagram commute. Okay. So we can prove a universal property, but we have to, I'm going to quickly introduce product uniform space. Product uniform space, given a family of uniform spaces, and dk is given in this pseudometric, family of pseudometric. Product uniform space is a uniform space xt, X is the product space of xk, and a family of pseudometric indexed by a coproduct of ik and defined in this way. Okay, then we can define product uniform space, and we can show that product of complete uniform spaces is complete. And also, we can extend the inclusion map from the product of uniform space into product of completion of each space. Okay, it's very easy. This is something like not a lemma, but a definition. Okay. And what I'm going to say is, if the index set of uniform space is discrete, that is, equality is decidable, then we can construct a uniformly continuous injection from product of completion into completion of product, satisfying this this condition. And also, using this lemma, we can show that if K is discrete, that is, equality is decidable, completion of product space is uniformly equivalent to how to say, product of completion space, completed space, okay? So therefore, we can extend the universal property for product space. Y D prime is complete, then any uniformly continuous or locally uniformly continuous mapping F, there is a unique uniformly or locally uniformly continuous mapping F tilde such that this diagram commute. Okay, so this is the construction of completion for uniform space with pseudometric. So I'm going to go on to the application of this construction. I'm not sure I have enough time, but I'll try to quickly start. So, application to integration theory, constructive integration theory. So we start with definition of semilattice. I think all of you know well about semilattice. So note that the layers forms semilattice with usual maximum operation. And for semilattice, we can make it partially ordered set with the ordering with this guy. And join is the least upper bound of this, the pair of elements. And vector lattice or Ritz space is a linear space L with a binary operation join such that L join is a semilattice and satisfy these three conditions. Classically, some condition, for example, the last one is superfluous, but we need this condition constructively. Okay. And the example of vector lattice, for example, C0R is the set of uniformly continuous function from R into R having compact support. Compact support is, there is the M such that outside of interval minus M, F vanishes, okay? So then C0R is a vector lattice with these operations, okay? So if a vector lattice is given, define a binary operation meet on L by this, then resulting structure is a distributive lattice. We can show that. And we can define positive part and negative part and absolute value of an element of L in this way. So this is the definition. An abstract integration space is a pair of L and E. L is a vector lattice and E is a positive linear functional on L. The linear and positive. For each F in uniformly continuous mapping with compact support, let EF be the Riemann integral. You can find how to compute Riemann integral in Bishop's book, for example. Then this pair is an abstract integration space. And in what follows, we fix an abstract integration space. Then it is easy to define on L a seminorm by this. Okay, seminorm is defined in this way. And then this seminorm induces a Schur metric ds in this way. So flux L d2 ds be a completion of metric space, this one. The equality of L is defined in this way, and we write iota L for inclusion map of L into flat L, okay? And we can show that addition, join, and meet are uniformly continuous from this space, uniform space, into complete uniform space. And the mapping, scalar multiplication, is locally uniformly continuous. Then using the universal property, it is quite easy to show that flux L is a vector lattice, okay? And also, E and seminorm are uniformly continuous. We can construct a uniformly continuous extension. This one, this guy and that guy. And integral F is called the integral of F, and the norm is called the norm of F. Okay, everything is defined by universal property, the universal property. And we can show that the usual property of integral, it is linear and positive and so on. And in particular, flux L is Banach lattice in the sense that this guy is a Banach space and satisfy this condition, okay? And second completion, this is the previous completion is just for metric, not uniform, family of uniform space. But the second completion is defined by a family of pseudometric. So fix U in L, du is defined in this way. Then du is pseudometric on L. M d tilde L be the completion of uniform space dl dl. The dl is a set of du indexed by u in L with the equality given by this one. And we write iota M for inclusion map, iota L. Something strange, but the inclusion map from L into flux M, okay? Then again, we can show that this is this L times L is a product space of the uniform space indexed by with a pseudo metric indexed by L. Okay. Then addition and join and meet are uniformly continuous, and scalar multiplication is locally uniformly continuous. Therefore, we can show that M is a vector lattice by the universal property. Of course, this addition and join, this operation has a continuous extension on M, so we can define a usual operation on vector lattice, and we can show using uniqueness condition of the universal property, which satisfy this structure satisfy the axioms of vector lattice using a uniqueness condition. So it's okay. And then we can show that there is a uniformly continuous embedding kappa from L to M such that this equation holds. And for each G in L, there is a uniformly continuous mapping phi to the G from M into L such that this equality holds. Okay. So now we have defined two complete uniform space, L and M. And we are going to define measurable and integrable functions over an abstract integration space. An element f of M is called measurable function over abstract integration space. And the net f lambda of measurable function converges in measure to a measurable function if f lambda converges to f in this uniform space. And the measurable function is integrable if there is the G in L such that kappa G is f. And we identify an integral function f and g with this guy. The integral of integral function is given by defining by integral of f is defined by integral of g. And the net f lambda of integral function converges in norm to an integral function f if f lambda as a net in L converges to f in L, uniform space L. And also this is quite natural definition. F lambda is increasing if mu is greater than lambda, then f lambda, f mu is greater than f lambda. Okay. Then we can show the following using the lemma. We have shown that let f be a measurable function, non-negative, and g be an integrable function, then their meet is an integrable function. And f is a measurable function, and if there is an integral function which bound the absolute value of f, then f is integrable. And also f lambda, let f lambda be a net of measurable functions converges in measure to an integrable function f such that f lambda is non-negative for each lambda, then meet of f lambda and f converges in norm to f. Okay. Using this lemma, we can show so-called Fatow's lemma. F lambda, let f lambda be a net of integrable functions converging in measure to an integrable function f such that f lambda is non-negative, and the integration of f lambda is bounded by a for each lambda, then integration of f is bounded by a. Okay. And we can also show the Roubaix monotone convergence theorem. Let f lambda be an increasing net of measurable functions such that f lambda is non-negative for each lambda. Then f lambda converges in measure to an integrable function if and only if each f lambda is integrable and integral of f lambda converges, in which case the integral of f lambda converges to integral of f. And also we can show dominated convergence theorem. Let f lambda be a net of measurable functions converging in measure to a measurable function f, and let g be an integrable function such that absolute value of f lambda is bounded by g for each lambda. Then each f lambda and f are integrable, and f lambda converges to, in norm, to f. Okay, so how to say, using compression of uniform space, in a sense, we can develop theory of measurable and integral functions without mentioning measure. And for example, complemented set and very technical, how to say, technical notions. But I'm not sure, because the notion of convergence induces classically topology. Therefore, convergence in measure and convergence in norm should classically induce a corresponding topology. So this work is going to capture this topology by a uniform space. Okay, but I'm not sure that the convergence almost everywhere could be captured with a topology or not. I don't know. Okay, so that's all, and this is the acknowledgement. So Tatsuji Kawai gave comments and suggestion on the first part of this talk. By the way, Tatsuji was staying in Uppsala when he was a PhD student, and Eric was there, and so he also learned Eric's good mathematics, I think. Okay, that's all. Thank you very much.
Thank you very much indeed. Let's give Hajime a silent applause as usual. So yes, any questions? Feel free to unmute yourselves as you ask questions, of course.
Yeah, I have a question. We know in predictive mathematics that point-free topology is also important. And for metric spaces, I did a point-free account of completion, and Eric showed that corresponded nicely to the Bishop's work, and in particular, that definitions of concepts such as compactness were equivalent on the two sides. Now, Tatsuji, I know, has done a point-free account of uniform.
Yes, yes.
So I wondered if you had any similar correspondences between your work and his point-free work.
How to say? It's difficult, but in my how to say, in my opinion, so topology with point and point-free approach to topology is something like function and polynomial. So polynomial represent function, but different polynomial represent same function. But the given topology with point can be represented by various point-free, for example, formal topologies. But formal topology gives the same point. So that means, for example, the big point, so I discussed with Eric, once I discussed with Eric, so in point topology with points, we cannot define compactness by high number compactness because it implies Fan theorem. But in formal topology, you can do that. I think, but I'm not sure how these 2 point topology with points and point-free topology is related with this work in this talk, but I think it's a very interesting topic to investigate. I don't know much about point-free version.
Okay, perhaps Tatsuji would have an answer.
Yeah.
Thanks.
Any more questions? I think we certainly have time for...
May I ask a question? Hi, Peter. Okay.
Yeah, Thomas.
So, Hajime, at the end, you mentioned a certain mismatch. Can that be interpreted as the following? I mean, in classical mathematics, for reasonable spaces, you have an equivalence between Daniel Stone measures and measures, yeah? And can one interpret this mismatch you mentioned at the end, where you're not sure that they are equivalent, but you were skeptical that this means constructively you don't have this equivalence between Daniel Stone measures and ordinary measures? I mean, Daniel Stone means a measure is monotone linear functionals on the space of observables, right?
I'm sorry, I don't familiar with Daniel Stone measure. So maybe I have to look into the material.
No, but it's very easy. Daniel Stone is very easy. You have a reasonable space X, and one says that measures on X do correspond to monotone linear functionals on the space, right?
Okay.
Because you certainly had something which you considered something which one could the Daniel Stone thing, and this was not the same as something else. But yeah, maybe it needs some more thought. Yeah.
Okay, thanks.
Thank you. I think we should wrap it up there for getting on to the next talk. So let's thank Hajime.
Peter, may I ask a question?
Yes.
So I'm curious, this notion of integrability that you develop, how does it correspond to the notion that you get if you go from like sigma algebras and like classical measure theory? The integrable functions, are they more, are they less Are there more integrable functions with your notion than the classical notion?
Okay, if you start with this example, this abstracting integration space and take compression L, then I think it's coincide with Lebesgue measurable, integrable function, L1 space, I think.
Right. Then I think I'm afraid we should wrap up there rather than go on with the questions. So let's thank Hajime again. And I'll just wrap up the recording and then we'll start again.